You already know this sound. You've heard it hundreds of times and never once actually listened to it. When water heats up in a kettle, it speaks before it boils. Not metaphorically, not as a casual observation. It produces a structured, reproducible acoustic sequence, one that rises, then roars, then pulls back into near silence. And that sequence encodes with a precision that has no right to exist in something as ordinary as a stovetop kettle, the exact thermal state of the water inside. The sound is a report, a continuous broadcast. Most people treat it as background noise and wait for the click. I came across this while reading something completely unrelated, a 1933 paper by a Dutch physicist named Marcellus Minnaert, who was trying to understand something different entirely, why rivers and streams make sound at all, not boiling water, running water. He wanted to know why a brook hums. He built a simple apparatus, blew air through a submerged tube into a bucket of water, and discovered that each bubble, at the moment it detached from the tube and sealed itself into a sphere, produced a sound of very definite pitch. Not random noise, a note, specific, reproducible, and determined. This is the part that stopped me, almost entirely by the size of the bubble. Nothing else. Not the gas inside it, not the temperature, not the pressure in any intuitive way. The bubble's radius. That was the instrument. I was 3 hours in before I noticed I had never gone back to what I was originally reading. And what stopped me from going back was a question that seemed so simple, it felt embarrassing. Too elementary to be the thing nobody had cleanly answered. Why does boiling water get quieter when it finally actually starts boiling? I assumed I knew the answer. I assumed everyone knew. I had never once tested the assumption. It turns out the explanation most people carry around, including the one I had, is incomplete in a specific and interesting direction. And the real answer points at something about the physics of trapped, collapsing spaces and the information hidden inside chaotic seeming sound that I am still turning over. I think I'm closer than when I started. Closer to a hard question, though, is not the same as close. Here is the architecture of what follows without the destination. First, what is physically happening inside a kettle during those 3 distinct acoustic phases? The early hiss, the pre-boil roar, and the sudden quiet at full boil. Because most accounts either skip the middle phase entirely or describe it at a level that misses the mechanically specific part, the part where things get strange. Second, what Minnaert actually proved in 1933, and why his result means that a bubble in water is essentially a musical instrument, a resonator with a pitch that follows a law so clean and so counterintuitive that it took him years to convince himself it was right. Third, what that second fact implies about the sound of boiling water, and what the scientific community has only recently begun to take seriously as a consequence. I won't tell you what the third part contains because I didn't know when I started, and the sequence in which you encounter the pieces genuinely matters to how the final idea lands. One thing before we go in, the standard account of boiling water sound. The one in most textbooks, the one I held for years, says something like, water heats up, steam bubbles form, they rise and pop, and that's the sound of boiling. The standard account is not wrong. It is the way a map of a city is not wrong. It is just drawn at a scale that makes the interesting parts invisible. What the water is actually doing in those three phases: before water boils, well before, starting at around 60 degrees Celsius, it begins to make a low, soft sound, a hiss that most people don't even register because it's quiet and continuous and easy to filter out while you're waiting for something else. This is not steam. The water isn't close enough to boiling for steam bubbles to form at the surface yet. What's happening instead is that cold water holds dissolved gases, oxygen, nitrogen. The ordinary atmosphere that entered the water at room temperature when gas solubility was higher. When you heat the water, the solubility of those gases drops. Oxygen and nitrogen become less willing to stay dissolved. They leave. They nucleate into tiny bubbles at preferred sites on the surface of the heating element. Scratches, microscopic pits, any surface imperfection where the geometry makes nucleation energetically easier. And they rise to the water and reach the surface more or less intact and pop gently. The sound this produces is around 100 hertz, a low murmur, nothing dramatic. The water is off-gassing quietly, the way a freshly opened bottle of something carbonated will audibly breathe if you hold it close enough to your ear. Then somewhere between 80 and 90 degrees Celsius, the exact threshold depends on the specific kettle geometry, the surface condition of the heating element, and how quickly heat is being added. The character of the sound changes entirely. This is the phase almost nobody describes correctly when you press them on it. At those temperatures, the heating element surface has become hot enough that the thin layer of water in direct contact with it reaches local boiling point, even while the bulk of the water is still significantly cooler. Steam bubbles now form directly on the heating element surface, not air bubbles. Steam. These bubbles grow, detach, and rise exactly as you'd expect, except they immediately enter water that is colder than the boiling point. And when steam enters sub-boiling water, it condenses. It turns back to liquid. And when it turns back to liquid inside a bubble, the bubble doesn't gently shrink, it collapses. Here is the word that carries the weight. Collapse. The collapse of a steam bubble in sub-boiling water is not a soft event. It is violent in a very specific way. When the steam inside the bubble condenses to liquid, the pressure support that was holding the bubble open vanishes in an instant, and the surrounding water rushes inward from all sides simultaneously. There is no preferred direction. The water closes on itself from every angle at once, and when it meets in the middle, it hits itself with the full momentum of the inward rush, which creates a pressure spike. This is called a water hammer. It is the same phenomenon, scaled down to a bubble, that causes the thunk in household plumbing when you shut a tap quickly. The moving water has nowhere to go and hits the closed valve inside a collapsing steam bubble in a kettle. This happens at a scale of roughly 10 microns or less, and it happens thousands of times per second across every active nucleation site on the heating element. Multiply one water hammer by thousands of simultaneous water hammers and you get the roar. That loud, aggressive sound that builds as the kettle approaches boiling. The one people associate with the water being almost ready is not the sound of boiling. It is the sound of boiling failing. It is the acoustic signature of steam dying in water that is not yet ready to receive it. The sound peaks somewhere between 1000 and 1500 hertz, solidly in the range of easy, uncomfortable hearing. And the amplitude is dramatically higher than anything produced during the earlier dissolved gas phase. This is the phase that 19th century physicist Lord Rayleigh described with some frustration in the theory of sound, noting that much remains obscure as regards the manner in which the vibrations are excited. He was right. It took high-speed cameras capturing at 30,000 frames per second for researchers to finally see clearly what was happening inside the bubble at the moment of collapse. And even then, the acoustic picture turned out to be more layered than the visual one. Then something unexpected happens. The water gets quieter, not a little quieter, substantially quieter. The full rolling boil, the thing you can see, the vigorous turbulence at the surface, the steam rising freely, sounds softer than the pre-boil roar that preceded it. People who pay close attention to their kettles find this counterintuitive in a way that stops them for a moment. If the boiling is more vigorous, why is it less loud? I was about to say this happens because the bubbles stop collapsing. That's not quite right, and the correction matters more than it might seem. What actually changes is the thermal structure of the water column. Through most of the heating process, the water is stratified, significantly hotter near the heating element, significantly cooler toward the top. The steam bubbles rising through that cold layer encounter water cold enough to condense them before they reach the surface. As heating continues, convection currents stir the water and the temperature gradient narrows. Eventually, the water column is hot enough at nearly every layer to support the rising steam bubble without condensing it. The bubbles survive the journey. They make it to the surface and pop gently. A soft release of vapor. No water hammer. No violent inward collapse. Just the murmur of surface popping. The silence is not the absence of boiling. It is boiling that has finally found water ready for it. The roar was the sound of the mismatch. The quiet is the sound of equilibrium. These are physically completely different events, and yet they produce, to most people's ears, only a difference in volume, which is easily interpreted as the boiling simply calming down. It is not calming down, it is doing something entirely different. What Minnaert actually proved. Let's go back to 1933 and the Dutch physicist with his bucket and his tube and his careful ear pressed to the experimental setup. Minnaert was not just observing that bubbles make sound, he was trying to prove a specific physical claim, that the pitch of a bubble's sound is determined by the pulsation of the bubble itself. The way the bubble expands and contracts at its natural frequency, rather than by any resonance of the gas inside it, as earlier researchers had assumed. The distinction is not trivial. If the sound comes from the gas resonating like a tiny, rigid-walled sphere, then temperature should matter a great deal. Because the speed of sound in the gas changes with temperature, if the sound comes from the bubble pulsating, the whole bubble expanding and contracting as a unit with the surrounding liquid acting as the inertial mass, then temperature should matter almost not at all, because it's the liquid that controls the system's inertia. And water's density changes very little across the temperature range from 10 to 90 degrees Celsius. Minnaert ran the experiment both ways. He changed the temperature of the water from 10 to 65 degrees Celsius. The pitch of the bubbles did not change. He then replaced the air inside the bubbles with hydrogen, a gas with a radically different density and acoustic properties from air. The pitch was identical. He used butane next. There was a small shift consistent with butane's different ratio of specific heats, but the shift was small and quantitatively exactly what the pulsation theory predicted. He changed the liquid from water to alcohol to a concentrated salt solution, varying the density by a factor of 2. The pitch changed in exact proportion to the square root of the liquid's density. Again, exactly as the pulsation theory predicted and exactly as the rigid resonator theory did not. The conclusion stated with the flat certainty of someone who has tested every alternative. Each bubble is a pulsating sphere, and the surrounding liquid is the instrument. The gas inside is almost irrelevant. What matters is the radius of the bubble and the density and compressibility of the liquid it sits in. The formula he derived, working from an elegant energy balance argument rather than the full fluid dynamics, is this: F equals 1 divided by the quantity 2 pi r multiplied by the square root of the quantity 3 gamma p naught divided by rho, where F is the frequency of the bubble's natural pulsation, R is the radius, gamma is the ratio of specific heats of the gas inside, P0 is the ambient pressure, and rho is the density of the surrounding liquid. Under standard conditions in water, this reduces to a clean and memorable relationship. A bubble with a radius of 1 millimeter resonates at roughly 3000 hertz. A bubble with a radius of 3 millimeters resonates at roughly 1000 hertz. Frequency is inversely proportional to radius. Bigger bubble, lower note. This relationship, now called the Minnaert resonance, is one of the most elegant results in the acoustics of liquids. It was apparently a mediocre paper when it was published. Minnaert himself was primarily an astrophysicist, and his work on bubbles sat quietly in its journal for years before the acoustic physics community absorbed it. It is now the foundation of virtually every quantitative model of boiling acoustics, sonoluminescence, research, and underwater acoustics. including the models used to predict how schools of fish affect sonar, because fish bladders are essentially biological Minnaert resonators. You might be thinking that this clean relationship applies to freely oscillating bubbles in open water, and that the chaotic, violent collapse events happening near a hot metal surface are different enough that the Minnaert equation doesn't quite apply. That objection is reasonable, and it turns out to be partially right, but it doesn't rescue the simpler picture. The collapse of a steam bubble is not a clean pulsation. It is faster, more asymmetric, and more violent than the gentle oscillations Minnaert studied. But the acoustic emission from that collapse still has a characteristic frequency content that is shaped by the Minnaert relationship. Because the bubble, even as it dies, still has a size and still has a surrounding liquid with a density, and those two facts constrain the frequency range of its acoustic emission. The bubble announces its size even as it collapses. It broadcasts its radius in its depth. And this is where something shifts from interesting to genuinely strange. What this means about the sound of your kettle. If each collapsing bubble emits sound at a frequency determined by its radius at the moment of collapse, then the acoustic output of a boiling kettle is not random noise. It is a frequency distribution, a spectrum. At each moment during the pre-boil roar phase, the sound your kettle is making is a superposition of hundreds of thousands of collapsing bubbles, each one broadcasting its size. The resulting acoustic signal is, in principle, a size distribution of collapsing bubbles, a real-time census of what is happening at the heating element surface encoded in sound. And bubble size during nucleate boiling is not random either. It is determined by the balance between the vapor pressure driving the bubble to expand and the surface tension and liquid inertia working to collapse. That balance is a function of the local superheat, the degree to which the surface temperature of the heating element exceeds the boiling point of the water just above it. Higher superheat produces smaller initial bubbles which collapse at higher frequencies. Lower superheat produces larger bubbles which collapse at lower frequencies. The acoustic spectrum of the boiling water is therefore a coded signal about the thermal state of the heating surface. Now, here is what I did not expect, and where the script I had written in my head for this topic turned out to be wrong. I went into this thinking the interesting part was the Minnaert relationship, the elegant physics of bubble pulsation. The 1933 paper, the counterintuitive result that the gas inside the bubble doesn't matter. That is interesting, but it is also within its domain essentially settled. What is not settled, and what a 2025 perspective paper in NPJ Clean Water describes as one of the most pressing open problems in the entire field of boiling acoustics, is the mapping from the acoustic signal back to the physical state. Not the forward direction from physics to sound, which is relatively well modeled. The inverse direction from sound to physics, which is not. You are probably expecting this to start wrapping toward a resolution. I thought so too at roughly this point in the research. Here is the second rupture, everything I described in the last section, the three acoustic phases, the water hammer mechanism. The Minnaert relationship, the frequency-radius connection, constitutes what researchers call the relatively understood part of boiling acoustics. The acoustic signals generated during boiling span from infrasound below 20 Hz all the way through audible frequencies and into the ultrasonic range above 20 kilohertz. And different events in the bubble life cycle contribute to different parts of that spectrum. Bubble nucleation generates high-frequency impulses in the solid heating element that propagate as elastic waves, detectable above 100 kilohertz. Bubble growth and departure generate lower frequency pressure waves in the liquid in the range of a few hundred hertz. Bubble collapse generates the dramatic mid-frequency components that dominate what your ear hears. But here is the problem. More than 99% of the acoustic energy generated at the liquid-solid interface reflects back into the liquid rather than transmitting into the surrounding air because of what physicists call acoustic impedance mismatch. The difference between the mechanical properties of water and air is so large that sound barely crosses the boundary. What your ear hears when you stand next to a boiling kettle is a highly filtered, heavily attenuated version of what is actually happening inside. The full acoustic picture, the one that carries the detailed state information, is locked inside the water. Measuring it requires sensors submerged in the liquid, or piezoelectric sensors pressed against the outside of the kettle wall, or specialized acoustic emission detectors mounted directly on the heating element. When researchers use those sensors, they find something that machine learning has recently begun to exploit in ways that should probably feel more strange than they do. The acoustic signature of boiling water contains enough information to distinguish between boiling regimes, natural convection, onset of nucleate boiling, fully developed nucleate boiling, transition boiling, the critical heat flux threshold, where the heating surface catastrophically overheats, with a reliability that exceeds most thermosensors. Not because the sound is simple, because the sound is structured, and the structure maps to the physics with a fidelity that emerges from the Minnaert relationship applied across millions of simultaneous bubble events. In nuclear reactor safety research, this matters considerably more than it does in your kitchen. The onset of nucleate boiling in a reactor coolant loop is a safety-critical event. Detecting it early, before temperature sensors in the fluid have had time to respond, before visual methods are possible in a geometry that no camera can access, could provide reaction time that the current monitoring architecture does not have. Acoustic emission monitoring of boiling inception has been studied for this purpose since the 1970s. The results have been consistently promising and consistently insufficient. Promising because the signal is there. Insufficient because Extracting a reliable state estimate from the acoustic signal requires a model of the boiling process that is detailed enough to be physically accurate and generalizable enough to apply across different reactor geometries, coolant temperatures, and surface conditions. That model does not yet exist in the form needed. Roughly 80% of the variance in the acoustic signal during nucleate boiling can be accounted for by bulk, temperature, and surface superheat. The remaining 20%, the part that would refine the state estimate from useful to reliable, has a specific and systematic structure that varies with surface roughness, dissolved gas concentration, flow velocity, and several other parameters in ways that are not yet cleanly separable from each other. The 20% is not noise. It is physics that the current framework predicts shouldn't produce a stable acoustic signature, but does. And nobody has explained why it's as stable as it is. That is the question. Not a poetic one, not a question about human significance or cosmic scale. A specific, bounded, technically precise question about why a class of acoustic features in subcooled boiling regimes is more reproducible than it should be given the turbulent, chaotic nature of the process that generates it. The answer, if it comes, will probably involve a more complete model of how bubble collapse events interact acoustically with each other, whether they add incoherently, which would produce noise, or whether they have a degree of phase coherence imposed by the geometry of the heating surface and the thermal gradient above it, which would produce the stable spectral features researchers are actually measuring. That coherence question is open in a way that is genuinely unresolved, not just poorly communicated. Deep learning the sound of boiling, training convolutional neural networks on spectrograms of boiling acoustics, has produced classifiers that can identify boiling regimes with error rates below 5% across multiple surface types and fluid conditions. These classifiers work. What nobody fully understands is why they work as well as they do, given what the physics says the signals should and should not contain. The network has apparently found features that the theoretical framework has not yet named. So I am back where I started, more or less. That kettle, the one whose sounds you have heard as background hundreds of times, is running a continuous acoustic broadcast. The hiss in the early stages is dissolved gases leaving as temperature rises. The roar is steam dying in water too cold to receive it. Thousands of water hammers per second, each bubble broadcasting its size as it collapses in frequencies that Minnaert derived from first principles in 1933 and confirmed in a bucket. The quiet of full boiling is not calm. It is equilibrium. The gradient is gone, the water is ready, and the bubbles finally make it to the surface intact. I understand those three phases better now than when I started, in all the ways that can be made precise and written down. What I understand less well is the part I initially thought would be simple, what the full acoustic signal is actually carrying, and why the information it contains is more structured than a turbulent, chaotic, multi-scale process has any obvious reason to be. The sound is not noise. What it is exactly is still being worked out.